Hello, this is Dr. Liu. In this video, I will review these three questions, chapter 18 from Pajodi, questions 3, 4, and 5. They are similar because they both ask, besides the system matrix and the cardinal points, they want you to calculate image and object relationship. They want you to find out images from the matrix. I know that there are a few pages in chapter 18, the first few pages, where something like this was discussed, but I want to use the full matrix method instead. So let's try to solve this problem just like the other problems I discussed in the previous video, using Python to calculate for all these, but we'll write down what we need. So we'll start from chapter 18, questions 3 first. So question 3. A biconcave lens has radii of curvature of 20 and 10 centimeters. Its refractive index is 1.5 and its center thickness is 5 centimeters. Describe the image of a 1-inch tall object situated 8 centimeters from the first vertex. So, in order to describe image and object relationship, we need to get the system matrix, and then we need to expand the system matrix in the matrix method in order to get the image. So let's first do just the lens. Okay, so we have biconcave, that means it's like this, 20 centimeters and a 10. So it's asymmetrical. So here's 20, here's a negative, actually positive 10, but negative 20. Got it backwards. Okay, and the thickness here is 5. So 5, index refraction 1.5. So we need refractive surfaces and what did I do? Okay, sorry. I said negative 20. Okay. So the first refractive surface is from here, the negative 20. So 1, 0, let's skip that. 1 over r, so 1 over minus 20. And then left index over right index minus 1. And here's left index over right index. So now I know where to put my 0 here, right above that. Makes it look organized. So that's the concave surface. And then there's a translation of 5 centimeters. So 1, 5, 0, 1. So that's a translation. And a second refractive surface, 1. And this is 1 over r, 10, and then left over right, so left is 1.5, right is back in the air, minus 1, and left over right, 0. Okay, so that's our three matrices. So just the lens, let's call that, or even ML, the lens. Okay, so this M is equal to R1, T1, then R2. All right. So we'll use Python to calculate. All right. We have already calculated a bunch of things over here. So we'll calculate more. This is question 3. So we'll do homework 3. Okay. Hit enter. So that's everything there. Okay, let's see. It printed out. Maybe I shouldn't have these things printed. Let me see. I think I wanted more printed out. There's only less than I needed. So what is going on here? And there's some updates, some changes. Okay, I added that. Okay, so let's look at homework 3. Alright, so this is homework 3. Okay, so here's, I got it. I should have calculated one more thing, which was just the system. let's do that. So see here we calculated that's the system matrix here. So if we just calculate the matrix of the lens, let's call that matrix of length. So that should be the R2 times T1 times R1. Okay, so let's see if that's correct. I'm looking at that. So R1 is at -20, and T1 is a 5, and R2 is the positive 10 of looking over here. So that looks right. And then I added some further distances just to do object-image relationship. So that's fine. But see here, I have the system matrix that I need to use to find the ABCDs. I don't really wish to go for more than that, but I just want to give you some ideas what they look like. So maybe I should just print this. I don't really need this. This is just the lens. It's not useful in the matrix method. But if you want to solve this, just like let's see. Let's not print it. Let's just do this line here. Okay, so we'll use that system matrix. What this does is it prints out the system matrix of just the lens, because you could use formulas based on the lens and the cardinal points, such as the focal length, to calculate for an object-image relationship. That's doable with some formulas. So let's save that. Okay, we just restarted the code. So now we actually have two sets of prints. Probably should add this line here, just a lens, right before this print, and then extended right before this print. That's okay, I don't really have to reprint that. So just the lens right here. So what you can do with this is you have focal length here, and you can do basically 1 over object, 1 over image, and you can find object-image relationship with an 8 centimeter object. So how far is the image using the thin lens formula, basically. And once you have that image, you can calculate the image object relationship, the height, well, the magnification, all from there. But I want to do it with the system matrix in mind. I'll do that after I do the system matrix method, which is you extend the system. So let's go back to the diagram here. So you have this as your current system, and you extend it because we're told there was an 8 centimeter object in front. There's an object in front, 8 centimeter in the front, and we want to find the image. So that is just for the just the length. Okay, so let's use that. And we do have a printout. So this printout is the first portion, 1.08, 3.33, 1.08, 3.33, and here 0.0792, 1.17. That's a 9. Okay, so that's that method, and you can get focal points and such. So that's one way to calculate, and the other way is expand the system, because we're told there was an 8 centimeter object 8 centimeters from the front vertex. So we actually have something like this. Come on. Whenever I want this to copy, it has its own mind. Okay, we'll place it here. So 8 centimeters, that's 5, so that's maybe 8. So 8 centimeters is 1 inch tall. So so height is equal to that. All right. So now our new system, in order to make object and image relationship, we have a new translation here. This T0 is equal to 1801. So we start our system as expanded. Our system starts now from this point. It has a translation and a refraction, translation, refraction, and then it translates into its final image. I know the image is not on this side, but I want to draw something that's familiar to everyone. Is here. We'll have an image relationship. This is kind of a distance I here, and this is where the image is going to show up. We're not even drawing this right. I know this is it's a concave lens, so it's supposed to show up on the left side, but I want this to be more understandable. So there's this eye here. So here is what this whole system is composed of. The T0, this space here, and this surface is it's R1. Oh, that's bad. It looks like a Q. R1, and that space translation is T1, and this refraction is R2, and then one more translation T3, which is equal to 1I01. So we don't know where the image shows up. We just say it shows up at location I. So that will be enough, and we can solve this equation. So our new system is equal to, well, we start from the very left, which is an 8 centimeter translation, and then we have a refraction R1, and after that through a translation of 5 centimeters, and then after that we have the second refractive surface, and after that we have the last bit of translation right here. So it involved this I here, and the good thing I'm using the symbolic pi, because symbolic pi can manipulate this I as an unknown, and then the system matrix will have I integrated, well, not integrated, incorporated in it. So let's see what this gives us in terms of okay, let's see, Python output. So that starts from this line PQRS, this line here and onward. So the system matrix is this A, B, C, D. Okay, so let's write that down. So A here is 0.0792. So 0.0792 I plus 1.08. And B is 1.8 I plus 12. And C is 0.0792, and D is 1.8. Okay, so if you go to this page, I'll give you a page number. I talked about this. The object and image relationship can be solved from the matrix. Let's see where that page is located. Okay, it is page 406. So page 406. What it tells you is, if you set B equal to 0, this gives you an object and image relationship. So B equals 0 is object image relationship. And also under this condition, once you have that, then the magnification is equal to A, which is the final height over the initial height. So all I have to do is to solve that equal to 0 for an I. That is pretty simple. So here's B. I wish I could use some sort of, let me try this. Yeah, highlighter here. I'm gonna do that, and I'll make it thin. So this is B. That's A. Mask dialysis C. And D. Okay, that's actually pretty nice. So if we set the B equal to 0, then we can solve for the image location. So here, 1.8i plus 12 equals 0. So I is equal to the negative. Of course, it's a diverging lens. It's supposed to have a virtual image on the left side. So negative 12 over 1.8. So that gives us, take a peek. Oh, actually, it's already here. I calculated that distance is negative 6.67. So negative 6.67. Is that right? This is 3 times a 3 times let's see, 1.6. This is 3 times 4. So 4 1. No, not 1.6. 3 times 6.6, and that's 3 times 4. Yeah, okay, I got it. So that is the distance, which means it's on the left side of this is measured from output plane, because that's how we constructed our system. From the output plane, extended that distance I. So it's from here, 6 1 6 1 to the left. So the 5 and here's 8. It's bound to stay here somewhere, right? 6.67 of distance. So you have a smaller image for sure. We're sure about that. We just don't really have the mathematical proof yet. So we'll have this thing here. So this tells you the location, and also we can calculate the magnification, which is just A here. Now that we know what I is, we just substitute that in, so that gets us that 0.0792 times negative 6.67, so that gets us a small number, and then plus 1.08. So that substitution has resulted in this, a positive quantity. So this number is less than 1, and then subtract that out of the 1, then you have 0.556 as the magnification ratio. So it is right side up is roughly 55%, a little over 50% height. So that compared to that, maybe I should just do this, have a whole grid, and have that taken up a little more than half the grid. So that's what it is coming from this side. So this is how to solve an object image relationship problem with the matrix method. So I probably don't really have to do this at all. I'll just do this in one shot. I place the object at a certain distance from the input plane, and then that distance is entered into one of the translation matrices, and then from the output plane to the image, there's another translation that's additional to this whole thing, the R, T, and another R. There's another T before, another T after. So then we can solve whatever we need. For example, if we have a known image location, we can solve for the object location. And the way to solve it is, once we have the matrix, and we set B equal to 0, that gets us the object image relationship. Whatever is unknown gets solved by setting B equal to 0. And once we have that, we solve the unknown, we put it into A, we can solve for the magnification ratio, which is that. And the other method would be, you just use the lens. So just the lens only goes this far, and you use the focal length, and to calculate, okay, that is in front of the first principal plane, and that is behind the second principal plane, and you can calculate object image relationship just like this. You can do in this example, you can do 1 over S1 plus 1 over S2 is equal to 1 over F, and the F's are the same, so you can find S2 equals da da da. And what is that measured in terms of the location? You have to reason what is that measured from. Is is probably measured from the second principal plane, not the output plane, right? So this is that. And if you look at the let's see, I'm looking at the solution. So they calculated this. So they found it was this is so S1 is equal to not 8 because we need to find how far it is from the front, the first from H1, right? From H1. So you got to calculate that, and let's see, we have. This is actually is 10.10. 10.1 is not the 8 because we need to find where the frontal plane is, and here the S2 is calculated as from H2, which is not the same as H1. So the answer was minus 5.61. So that's from H2. So where is that exactly is H2? Well, you don't really know. Then if you calculate that from vortex 2, which is the output plane, then you get minus 6.67, something that we already did. So I thought the this way is better because this is completely algebraic, and you get a matrix by looking at it. Yeah, you can look at it this. You get a matrix, and then you just do algebra. You can solve things out. You don't have to think about how do I get that principal plane out, and get the principal plane out, convert the distance from the object to the first the input plane or first vertex to object from first principal plane, and then get the output to convert from the second principal plane to the second vertex instead, so that you can get something physical distance that you can confirm on the experimental setup. So that is my preference, is to do entirely in the matrix method. So let's see. Okay. Well, this way don't have to scroll too hard. All right. So that is one question. So let's go through the second one here. Question number 4. So question number 4, an equiconvex lens having spherical surfaces of radius 10 centimeters, a center thickness of 2 centimeters, and a refractive index of 1.61 is situated between air and water. Water has n equal to 1.33. An object 5 centimeters high is placed 60 centimeters in front of the lens, and find the cardinal points for the lens and the position and the size of the image formed. So this time we do have to calculate the length matrix so that we can get the cardinal points from just the lens. So okay, we'll do just the lens, and it is an convex. So there's not just convex, but equal radii. So here's 10, here's minus 10, radius of curvature, and the thickness is 2. Index refraction is 1.61, 2 centimeters. Okay, so now we know 1.61 is index refraction. So we'll calculate these 1. Here is 1 over 10, and in left over right, okay, left is 1, right, far right is that 133, minus 1, left over right, 0, so that's our R1, and T1 is equal to 2 centimeters, 1201 thickness, and R2 is equal to 1, here 1 over negative 10, and the left is 1.61, right is 1.33, minus 1 over left divided by right, and here's 0, so that's R2. So M of the lens is just R2, T1, and R1. Okay, since we're also asked about the object-image relationship, I think it's best if we do the calculations by extending this into, we know there's a 60 centimeter distance in front. I'm not going to draw to scale, so I'll just do a little bit pretending to draw that. Okay, oh man, okay. Copy, paste. Okay, so now we have an object 60 centimeters. Apparently we're looking for an image behind, so some eye distance away from the output plane we have something that may look like that. Alright, so the expanded system has this T0, and here's R1, T1, R2, I didn't do the script curly thing, and here's a T2. Okay, 0, 1, 2. Alright, so we have expanded in front and behind, so T0 is equal to 1, 60, 0, 1. And then T2 is equal to 1I, 0, 1. Okay, this problem has its own unique feature because there's different media here, so the focal lengths here and here are different. So if you want to use the matrix, not matrix, excuse me, the thin lens formula, then you must have two different foci, focal lengths included in that. There's a formula in the beginning of the chapter 18. You can look at that, but I'd rather not do it. I'd rather just do it in the matrix method alone. So I was asked about, let's see, the question says, find the cardinal points. Okay, so here we can get P, Q, R, S, V, W, F1, F2. Alright, so we can get all of these, no problem. It'll just take time. And from here, this is an expanded system. We're not looking for that anymore. We're looking for the whole system matrix expanded, which is T2 here, and just the length, and then T0, right? So you're expanding that before the lens. Let's see. Okay, I don't think it's a good idea to do that. I think it's a good idea to do this. T2, and what is that? R2, and then T1, then R1, and R1 is left multiplied with T0. So close parentheses, close and close. Okay, so we got all the parentheses. Alright, so I don't think it was a good idea to have this in the middle because that's the wrong order operation to multiply. Alright, so back to here. And we just multiply them all together. And this will incorporate the I into the calculation. So we're going to take a look at our output from Python. So the second half is a PQRS. So it seems like P is not really related to it, Q and some other things. So you can look at the this whole thing here. Is that let's see. Actually, it's number 3. Sorry, let's do number 4. Okay, so that's number 4. So extended system, and we have the A, B, C, D. So that's A is related to I, and B is related to I. Okay, C and D. So do we actually need anything more than A or B? No, we don't, because B equals 0 gets us the relationship, and A equals the magnification. So we just need those two. So let's write this down. Point 924 minus 653i, and B is 56.7 minus 3.19i, and C is negative 0.0653, and D is negative 3.19. Okay, so that's our B. We just need A and B. So B equals 0 gives us the object-image relationship. So that gives us 56.7 minus 3.19i equals 0. So that gets us the image I is going to be, okay, I solved it, 17.7, 17.8 centimeters behind the vertex V2. Because that's how I defined I, is by expanding the system from the V2 here, or the output plane, to the right, I distance. If I calculated that as a different distance, that would be a different result. Okay, anyway, so now we have I, and the A, which is equal to the magnification, is equal to 0.924 minus 0.0653 times this I, 17.8. I already calculated that image size. Actually, not image size, I think that's image magnification. So 0.235. Okay, so if we have the image object size, we can calculate image size. The object size is a 5 centimeter object, so y of the image, how about that? Is 5 object times 0.235 negative. So it's like times 10 over 2. So negative 2.35, 1.18 centimeters tall. So it's upside down like I was guessing it. So let's see, question 4, 1.18 and minus 2.235. So I think this idea of expanding the system and solving the expanded system for object-image relationship is pretty linear algebra or algebra-ish, and the other way is a bit more geometrical. Think about geometry, think about how to do the equation, especially with two different media on either side. You must use this. So let's see. So F1 over S1, so it's probably a negative, plus F2 over S2 is equal to 1. I think that's the equation. And then once you calculate the S2 out, it is related to a virtual, an imaginary plane called the H2, and you're better off calculating that distance from a physical surface so you can do your measurement with, right? So this method is not preferred. I like this method a lot better. Okay, so I think time is running pretty fast. We have one last question, number 5. So let's get that done. So we'll finish this video. So number 5, a hollow gas sphere of radius 10 is filled with water, and you can ignore the glass. And for the parallaxal rays, determine the cardinal points. Okay, so it looks like we have to calculate that. And then calculate position magnification of a small object 20 centimeters from the sphere. And then you also want to draw a diagram. What else do you want, right? Okay, so it's a sphere. Alright, so we have sphere, and it has a 10 centimeter radius, so the thickness is 20, and the front surface is 10 centimeters here, back surface minus 10 centimeters, and radius of curvature, and we have an object that is 20 centimeters away. Okay, so again we're going to calculate just the length or the water, 1.33, and then we'll expand the system and find the image because it wants me to do the just the water. So I'll expand a distance of I, and I expect something that might show up like this, but probably not. It's gonna show up over here as magnified. This is what in the old days, um, if someone wants to sew something and couldn't see the details, like a grandmother, they would actually take a fish, like a fishbowl, glass fishbowl, fill it with water, and have this in between themselves and their sewing work, so that they could see a magnified image. I'm pretty sure this is actually going to be over here a magnified version. Anyway, this makes it more generic and easier to look at. Okay, so we have all these, and R1, right, has I'll still keep writing these out. 1, so here's a radius of curvature, and the left side, right side, minus 1, left side over right side. T1 is equal to 20 centimeter. Oops, that's wishful thinking. Well, no, 20, 0, 1. Okay, that's just in itself simple enough. R2 is that back surface, so -10 is a 1, and then left is 1.33, right is air, 1, minus 1, and 1.33 over 1, 0. And then we're also going to add some T0 here, which is 120.01, and the T2 here, which is 1I01. So just the length is going to be R2, T2, T1, R1, and the whole system, it starts with the ends with T2, then R2, then T1, then R1, and T0. Okay, so I think I got all the parentheses. So that's the whole system, and that's equal to something, and with that something I can calculate ABCD, right? Again, now I don't even want to put the numbers or expressions in. So B equal to 0, that gets you object and image relationship. You can solve for I. And then take I, plug that into A, so then A is equal to the magnification ratio. Okay, so let's take a look at Python. So we're solving for question 5. Okay, again, extended system, just the lens. So if you need just the lens, these are the cardinal points right there. If you need the system has this A, B, C, D. And again, A and B are dependent on I, C and D are not. Then calculating the image is basically setting this I equals 0. You can solve for this a B equals 0, solve for I. And you find the image distance 51 centimeters away, positive. From let's see, right. I think my other self was wrong, and the old granny would actually have the object much closer to the fishbowl than 20 centimeters. Actually, it would be the sewing work would be almost stuck against that surface. Okay, so I'm wrong about that. But this situation is just like this. 50 centimeters to the back of V2, and that's a bit further away and also magnified to twice as big. So with that number there, right? Thank you.